Hello everyone, welcome to my quantum mechanics lecture number 4. In the last lecture we talked about mainly linear operators, where an operator is by defined is this. An operator is an operation that takes a vector and gives us another vector. So transform it into another vector. So in this lecture I will start with active and passive transformation. Active and passive transformation. Let's look at this transformation. Let's say we have a ket V and we transform it by using this U operator. And so the matrix element of any operator, right? Matrix element of any operator is given by this thing. So and matrix operator of matrix, this thing is given by this. So from here we can write this. So it is clear that some change would be effected if we left the vectors alone and subjected all operators to the change, right? We can also do this and get the same result. Okay, so the first case where we change the vectors, state vectors, we call it active transformation. And another way to see an operation is to just change the operator and act on the original vectors. This is called passive transformation. So the present nomenclature is in reference to the vectors. They are affected in an active transformation. I have left alone in the passive case. The situation is exactly opposite from the point of view of the operators. So in quantum mechanically, active and passive transformation provide us with same physical transformation, but two equivalent ways of describing the same physical transformation. So we can say one transformation is like this, that the vectors are changing, or we can also say the operators are changing when we do any physical transformation. So this is another way to see how or represent transformations. Now the central, very important topic for quantum mechanics, called the eigenvalue problem. Consider any operator omega is acting on any ket V and giving us just some number into V. Okay, if it is given by this, then we call this V ket eigen eigenkets of the operator omega with eigenvalue small omega. Let's just to differentiate between operators and scalar value, let's put a cap on the operators. So this is the eigenvalue and this is the eigenkets. So it just whenever an operator just scale up a vector, this operator with an random scalar, we call that vector eigenket of that operator with eigenvalue omega. So what are the some examples of eigenvalue or eigenket? Some examples of eigenkets. First, the identity operator. It just any vector, the eigenvalue is 1. And all vectors, any vector, follow this rule. So all vectors are its eigen vectors with its eigenvalue 1. And let's take another operator. Let's take the projection operator in any direction of V. Okay, so this is the projection operator. The projection operator associated with a normalized ket V. So that means if we operate this operator on some vectors V, it will give us the what is the projection of that vector in the direction of V. So if we have any vector, let's operate in with this vector, and we should remember this, the projection operator is like this. So if we do this, we write this, the alpha will be, we will find this, and if V is normalized, so this is 1, so we will get alpha V. That is again alpha B. So in this case the eigenvalue is 1. And if we if we operate this projection operator on a eigenket on a vector perpendicular to ket V, we'll find out V. So if they are perpendicular or orthogonal, so the inner product between them is 0, so this will give me 0. So eigenvalue is 0. And if we project the operator, operate this operator on linear combination of V and perpendicular of the V, we find out that this gives us just alpha V. So this is not an eigenvector, not an eigenket or vector of the projection operator. These are some examples, two examples. We saw first the unity operator and then the projection operator. Another example will be the rotation operator given by this. So this operator rotate any vector anti-clockwise with respect to our x-axis, and we know the operation of this. So unit vector in the direction of x direction is unchanged, and we got this. Okay, so these are the examples of, so here eigenvalue is 1. So generally if we have any eigenvector, we can also have so any scaled up vector of vket is also an eigenvector of our operator omega. So we will treat the whole set of vectors in one direction as one eigenvector. So we will not treat the multiplication of eigenvectors as distinct eigenvector. We will only say this is the eigenvector. It is determined by our choice. We can say any vector in this direction can be an eigenvector, and will not treat every eigenvector as distinct. So now one question is, how many eigenvectors are there for our rotation operator around x-axis? How many eigenvectors are there around x-axis? So from our intuition, it says it would be 1. Just the vectors along x-axis that will not change. But it has two other eigenvectors in V. See, in complex vector space, it has also two other eigenvectors. So from our intuition, we can be wrong. So we need a reliable and systematic method for solving any eigenvalue problem for n-dimensional complex space, vector space. So now our target is to develop a way to how to figure out how can we determine the eigenvector and eigenvalue of any operator in complex plane. So this is the eigenvector equation. If we multiply by unit operator, its identity operator is change nothing, so we can write like this. So operating both sides by this matrix, assume it exists. Assume it exists. We can write V but we cannot operate on zero factor and find something. So our assumption that inverse of this thing exists is wrong. Okay, and so and from linear algebra for any matrix we know the inverse of any matrix is cofactor of transpose of that matrix divided by determinant of that matrix. So if it does not exist, that means the determinant of this matrix must be 0. So our determinant of this matrix must be 0. This is the condition for non-zero eigenvalue. Let's see how we can figure out this. Now if we want to have the matrix element of this operator in V unit the I can be written, the identity operator can be written by this. We have used this thing, the identity operator is this. Now let's do this, this one into this one. So I operator phi j minus omega I into j, and this whole thing is into that. So it will be out of the sign, it will be 0. And what is this? This is the matrix element of our operator omega. So you can write like this, matrix representation, and this is just Kronecker delta, and this is the component of V along Z, and this is so if we solve this matrix equation, we can easily find what is omega. So if we do the determinant, and we will get an equation like this where our omega will be some coefficient into some power of omega, and it will give us 0. So this equation is called characteristics equation. Characteristic equation, and we can write this polynomial as polynomial of omega like this, where m equal to 0 to n Cm omega m. This polynomial is called characteristic polynomial. So omegas are basis independent. Means no matter what basis we use, we will find omegas, and the omegas the omega will be always same, the eigenvalues will be always same, because from the characteristic equation, and we find this is any vector v, so these omegas eigenvalues are basis independent. No matter what our basis is, it will always give us the same answers. And from the as we retain this polynomial, and here m from 0 to n, so we know that we will find n roots of omega, n roots. So we can say every operator in V and C, n-dimensional complex vector space, has n eigenvalues. Now we set up a procedure how to find the eigenvalues of any operator. Let's see an example. So with the matrix representation of our rotation rotation operation at x-axis is given by so we will figure out eigenvalues and eigenvectors for this operator. So we need to take the determinant of r minus omega I. It will be 1 minus omega 0 0 0 minus omega minus 1 0 1 minus omega, and it will be equal to 0. So if we just expand the determinant, and we'll find this. From here we see that omega has three values, 1 and plus minus I. So there are three eigenvalues, one is 1 and another 2 is plus minus I. So for every eigenvalue there will be an associated eigenvectors. Let's figure out this. Let's say for 1, for eigenvalue 1, in matrix form we can write 1 minus 1 0 0 0 0 minus 1 minus 1 0 1 0 minus 1. This is our eigenvector. It will the inverse will act on this vector and give us 0 vector. So if you do the matrix multiplication, and we will find out these two answers. So x2 and x3 are 0. So x1 can be any value. So the expected form of eigenvector will be x1 0 0, because x2 and x3 are 0, we can write is x1 1 0 0. So it can be anything, we will choose x equal to 1. So the eigenvector is 1 0 0. Normally we take the normalized vector, but this is already normalized. It has modulus 1. Okay, now for the second one, for the I, what will happen if this is I? The equation will be 1 minus I 0 0 0 0 minus I minus 1 0 1 0 minus I, acting on our eigenvector, let's say x2 x1 x2 x3, it will give us the 0 vector. So if we again do the matrix multiplication, and we will find out these are the equation. From here we can see x1 is 0, x2 is I x3, and x2 is I x3. So this was our vector. If we put in the values in here, we'll find out 0. Let's take I x3, and x3 is x3. So if we take x3 common, we'll find out this. This is our new eigenvector. Again, x3 is upon ourselves, we can use anything. So if we take the normalized version, if we normalize it, so it will be 1 by root 2 0 I 1. This is our desired eigenvector for omega equal to I. This eigenvector can be written, we are using a new notation. The eigenvectors can be written in this way. Similarly, for omega equal to minus I, we can show this is our eigenvector. So this is the procedure how we figure out what are the eigenvector and eigenvalue of any operator. Let's now we are familiar with eigenvalues and eigenvectors, so we need to study some properties and theorem about eigenvalues. Theorem number 9, and it is very important for quantum mechanics. Theorem number 9 is the eigenvalues of a Hermitian operator is real. Let's prove it. Let's say this is our Hermitian operator, gives us a number, and if we do this thing, it will give us this. Now take the adjoint of this thing, we'll find out omega is this, but we know Hermitian operators by definitions are equal to their adjoint. So by that logic we get and if we can write this cannot be 0 because you cannot operate on any 0 factors, so cannot be 0. So omega is omega conjugate. So if the conjugate of any complex number is equal to omega, then omega is real. So the eigenvalue associated with Hermitian operators are always real numbers, not complex number. Theorem 10. To every Hermitian operator, omega, there exists at least a basis consisting of its orthonormal eigenvectors, and it is diagonal in this eigenbasis and has its eigenvalues as its diagonal matrix. So basically it's saying if we have Hermitian operator, all the eigenvectors of the Hermitian operator will always be orthogonal to each other. And so we can form a basis with those eigenvectors. And if we express our vector space in those eigenvector in those bases, the matrix form of our Hermitian operator will be always a diagonal matrix, and the values of the eigenvalues will be on the diagonal of that matrix. So let's prove it. So let's say our characteristic equation has only one root. We are denoting that one root with omega 1, and for omega 1 there is an associate eigenvectors omega 1. Get omega 1. So the perpendicular vectors of all the perpendicular vectors with orthogonal vectors with omega 1 reside in a subspace n minus 1. So subspace of all vectors orthogonal to omega 1. So to prove, let's choose our basis, the vector so let's choose our first basis is our first, and it is normalized to unity. and the remaining bases are n minus 1 orthonormal vectors reside on these spaces. So in this basis, our matrix representation of omega will be rho 1 0 0 0 dot dot 0 0 0 0 dot 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 0 and something. The first column is just the image of omega 1 after omega is has acted on it. So it will must be 0 all the thing, and for Hermitian matrices operators, for Hermicity this row must be also 0. So we can write our omega operator like this. It will be any matrix, and this is the first row and first column. So the characteristic equation for this matrix looks like this. Equation has the form omega 1 minus omega n determinant of boxed submatrix equal to 0. So any determinant of the submatrix, as we have seen, can be represented like this in a polynomial. Okay. So this is the polynomial of n minus 1 omega equal to 0. So as we know, this polynomial must also generate second root omega 2 and an eigenvector like this, omega 2 ket. We will define the subspace, another vector space that is perpendicular to 2 and has n minus 2 dimension, and the orthogonal to omega 2 ket vector will is automatically orthogonal to omega 1. So this is orthogonal to omega 2 and omega 1. So by repeating the procedure from above, we can easily write in matrix form. The first one will be this, zero, and the subspace V n minus 2 orthogonal to 1 and 2. So by the same logic, again and again procedure, if we follow the procedure, we will find out our matrix looks like this. So the operator can be written in a diagonal matrix in matrix representation, and the basis of eigenvectors are orthonormal. This is our proof. So if we look into theorem 10, it says it at least have one. Okay, at least have one. That means there can be more bases, more than one basis, where the eigenvectors are that eigenvalues are vectors our phi operator. So when will we find more than one basis of eigenvectors that diagonal is our operators? So this is called something called degeneracy. So what is degeneracy? If a single eigenvalue represents more than one eigenvector, then the phenomenon is called degeneracy. So suppose we have two eigenvalues that are equal and they represent two different eigenvectors. Let's say omega 1, we find out omega 1, and also find out. So what does it mean? So it follows that if you take linear combination of these two eigenvectors and operate on them, on the linear combination, we get this. So the linear combination of our two eigenvectors is also an eigenvector of our operator. So this whole space that is spanned by this omega 1 eigenvector and omega 2 eigenvector is also our eigenvectors of our operator with eigenvalue omega. So this whole space is called, this space, that is space is called eigenspace of our operator. So whenever we have degeneracy, we will have an infinity of orthonormal eigenbases. The choice is on ourselves. We will take any two vectors from this eigenspace to represent our eigenvectors, orthonormal eigenvectors. So in face of degeneracy, we have an infinity of orthonormal basis. not orthonormal eigenbasis. So let's do a problem on this thing. When we have degeneracy, we have infinite number of eigenvectors. Let's see this. Now consider an operator given by the matrix representation 1 0 1 0 2 0 1 0 1. So we have to show that it has an infinite orthonormal eigenvectors. We'll solve it. So the determinant will be 1 minus omega 1 0 2 minus omega 0 1 0 1 minus omega equal to 0. If we expand it, find out 1 minus omega into 2 minus omega into 1 minus omega minus 2 plus omega equal to 0. So after some algebraic calculation, we find out this. So our omega has 0, 2 and 2 values. So you have to find out 3 eigenvectors. So let's for the omega equal to 0, the matrix form is zero. So if we solve this, if we do the matrix multiplication, we'll find this 3 equation. So x2 is 0 and x1 equal to minus x3. So any vector in the form of x1 0 x1 minus x1 is eigenvector. If we normalize it, we just have to divide it by its magnitude. If we normalize it, we'll find the eigenvector corresponding to the eigenvalue 0 is 1 by root 2 1 0 minus 1. So this is our one eigenvector. We have to find another 2. So omega 2 we'll find out x1 plus x3 equal to 0, x1 minus x3 equal to 0. So x1 equal to x3. So notice that we did not know x2 is unknown. So it can be anything. It can be anything. So we find out that if we choose, it is on our, if we choose, let's choose x2 equal to 1. So we find out that our eigenvector corresponding to, one eigenvector corresponding to 2 is 1 1 1. Now the third vector is just find out the, so we need another orthogonal vector. So and the third vector is now chosen to be orthogonal to this, and by simple calculation we will find out this will be 1 by root 6 1 minus 2 1. So that's how we can find out the orthogonal vectors, eigenvectors of in case of degeneracy. Some important thing in case of degeneracy, omega I, ket omega I no longer refers to a single ket, but to a genuine element on the eigenspace Vmi omega I. To refer to a, if we want to single out a particular value, element, if we want to refer to a particular element, you will use the symbol like this. So where alpha will labels the ket within this eigenspace. So this was the degeneracy and eigenvalue problem of any operator. Now new theorems. Theorem 11. The eigenvalues of unitary operators are complex numbers of unit modulus. The eigenvalues of a unitary operator are complex numbers of unit modulus. And theorem 12, the eigenvectors of a unitary operator are mutually orthogonal. For these two theorems, we assume there is no degeneracy. So our next target is to prove this two theorem. So we will prove these two theorem together. Let's take the unitary operator like this on any eigenvector like this, and the same unitary operator acting on uj ket give us this. So if we take the corresponding bra form, we'll get this. Now the inner product will look like this. By the definition of unitary operator, this is the definition of unitary operator. So we got uj identity operator u. Okay, this will be I and this is j. J, this is I. So ui uj is given by this. So uj into ui equal to this from here. You can write equal to 0. So now if I equal to j, so just simply give us so we can say there is 1, and if I is not j, then ui, the inner product, f0. So this proves us, the first proof, that the unit operator has complex number, eigenvalues of complex number that has unit modulus, and the second one proves that they are orthogonal to each other. So we today in theorem 10 we saw that if we have any Hermitian operator, we can represent it in diagonalization matrix. So what does it tells us in terms of active transformation and passive transformation state? So let's say operator u change any basis to the eigen basis of operator, Hermitian operator phi. Omega, sorry, phi omega. Let's say this. So we can write this and bar from so if we do this omega, we find that so this is the matrix element of omega in the basis of the eigenvectors. and this is the matrix elements of this matrix in any matrix I. So we can see this in two different ways. This is from the active transformation and this is from passive transformation. So the active transformation statement will be every Hermitian matrix on any complex n-dimensional complex vector space may be diagonalized by a unitary change of the basis. Okay, and passive transformation statement will be any operator is a Hermitian matrix. There exists a unitary matrix U such that this operation is diagonal. So U is built out of the eigen vectors of omega. So let's do a problem with Hermitian matrix. Consider four Hermitian matrices M1, M2, M3 and M4. Let's say there are four Hermitian matrices that follow this rule. It's just given where I and J go from 1, 2, 3 and 4. The first problem is show that the eigen values of mi are plus minus 1. So let's say I equal to j. So if I equal to j, then from the given equation we find out this is 2mi, the Kronecker delta of del ii is 1, so this is 2i. So mi into mi would be identity matrix. Therefore if we apply this operator on any vector, any ket vector, as this is a Hermitian operator, we will find out this, and finally mu square omega. But this is identity matrix, so this will be equal to omega. So omega square is equal to 1, omega equal to plus minus 1. So the eigenvalues of these Hermitian matrices are plus minus 1. Second one is by considering this relation, we have to show that mi's are traceless, that the matrices are traceless. So let's say mi, mj, mi. If we apply another mi in front of them, they look like this. So from 1 mj into mj is basically identity matrix, so this gives us mi. Now if we take the trace, mi is minus trace mj mi mj mi mi. This is equal to trace mi mj mi. We have used this notation. So this will be trace mi. So we find out that trace of mi is equal to minus trace of mi. That is not possible, so it must be 0. Now problem 3. Show that they cannot be odd dimensional matrices. The dimension will be even numbers. So trace of mi from number 2 is 0. We found out that. The trace will be the summation. If we can diagonalize any vectors, and we know the diagonal entries of the matrices are Hermitian matrices are our eigenvalues. So this will be like this. As omega is plus minus 1 only, so if n is odd, it is not possible to get sum of all the eigenvalues and get 0. So n must be even. So we have studied diagonalization of Hermitian operators when there are only one operator. What happens if we have two operators? So our next topic is simul. So we will now start theorem 13. If omega and del gamma are two lambda, omega and lambda are two commuting Hermitian operators, there exists at least a basis of common eigenvectors that diagonalizes them both. This is our theorem. So let's prove it. Let's say this is our eigenvector of omega. Let's non-degenerate, let's say non-degenerate. And if we apply this, we'll find out this. So as they are commutating, so this is equal to this. So we can see that this is also an eigenvector of omega. So it must scale. It must scale. So our lambda operator must scale our omega I, as there is no degeneration. So this ket, omega I ket, is also an eigenvector of our lambda with eigenvalue of lambda I. Since every eigenvector of omega is eigenvector of lambda, it is evident that this omega basis will diagonalize both lambda and omega. Since omega is degenerate, there is only one basis with this property. So this is the proof for non-degeneracy when omega is non-degenerate. But what if both operators are degenerate? So if operators are degenerate, let's say our omega operator can be written like in matrix form. This can be written like this. This will be 0, this will be 0, this will be 0. So in every eigenspace denoted by this, corresponding to the eigenvalue I, there exists an infinity of bases, as we know this. So let us arbitrarily pick let's say this is the vectors we are picking. They are both orthogonal. Now if we do this operation, as they are commutating. So we got this. So again we can say this is also an eigenvector of our phi operator. So due to generacy, this is not a single vector, there are multiple vectors. So due to generacy, this is also generacy. So due to degeneracy, alpha lies in VMI, our subspace VMI. That subspace is given by this. So omega, if we take this inner product, we will find out it will be 0 because this eigenspace and this eigenspace are orthogonal to each other. We know the different eigenspaces are orthogonal to each other. So in this basis we will find out some matrices like this. Like this. This can be represented like this. So it is called a block diagonal matrix, obviously because there are blocks in the diagonal. The block diagonal form of lambda reflects the fact that when lambda acts on some element, acts on some eigenspace element, it turns it into another element of that space within its subspace I. Our lambda is given by the matrix lambda I, which appears as a block on the above matrix. So as lambda is Hermitian, so lambda i's are also Hermitian. So it can obviously diagonalize by trading the bases. Right. That we started with. For the eigenbasis of lambda I, let us make such a change of basis in each eigenspace, thereby rendering lambda diagonal. So we'll find finally that lambda is represented by like this. Where lambda 1, lambda 2, lambda 3 are the eigenvalues of lambda i's. So if lambda is not degenerate, the above case was for degeneracy, but if it is not degenerate, so lambda I within any subspace, this will not be equal. So for any k li, we will find out unique vector. So the freedom omega gives us, because that is degenerate, is fully eliminated by our lambda operator, because lambda is not degenerate, so it has unique basis. So new notation in this case, our case will be represented by this, where omega and lambda, omega is the unit vector, orthonormal vectors of orthonormal eigenvectors of omega, and lambda will specify which values we will take. So if it is degenerate, let's say only two values are same, there is a two-dimensional eigenspace from which we can choose any two orthonormal vectors, as we seen for degeneracy. If we want a unique basis, we need a third operator that commutes with both our omega and lambda operator and non-degenerate in the subspace. So like this case, if we want to have a unique basis, we need another Hermitian operator that commutes with both omega and lambda and not degenerate, so that we can figure out a unique basis. Okay, today's lecture is done here. If you have any question, please write them in the comment section.